Live from the BBC, The Naked Scientists.
Now, it's an embarrassing but somewhat true fact that we know more about the surface of the Moon, and perhaps even the surface of Mars, than we do about what lies beneath the surface of our own planet's oceans. But this week, we're going to hopefully lift the lid, scratch the surface, and shed some light on the deep, mysterious depths of what's going on down there with the help of our guest, Dr. Jason Hall-Spencer from the University of Plymouth. Good evening, Jason.
Hello there.
Also, Ron Douglas has come in from City University in London. Hi, Ron.
Good evening.
Thank you for coming in. And we'll be joined on the telephone later by David Klein. And we're going to literally explore what's lurking in the depths. But that's not all we've got in store for you. Hello, I'm Chris Smith. Also here is Phil Rosenberg.
Hello, everybody. Also tonight, we're going to have new way to detect speeding drivers just from the sound that the car's making, and also new ways of safeguarding Earth's fuel supplies in the future. Now, also tonight, we've got kitchen science, as ever. This week, we're going to be looking at how to make your very own submarine at home. And the prize for that is the Oxford book, Living Science. Now, I've got it in front of me here. Looks absolutely fantastic. Everything you could really possibly want to know about science in the modern world. Great prize. So, if you've got any science or technology questions, or if you want to give us a call for Naked Sciences, just give us a call, 08459 25 2000, or chris@nakedscientist.com.
And just to recap, the first half of the programme, we're taking any science question on any subject. You just have to get on the telephone, or you can email me. It's chris@nakedscientist.com. That phone number, as Phil said, 08459 25 2000. And also, phone in now if you do have any questions about the deep sea and exploration of the oceans, and we'll put that to our guests once we start talking to them in roughly 10 or 15 minutes. Now, who's been caught by a speed camera in this room? Have you? Have you guys been caught for speeding?
I have. Hopefully I didn't on the way here today.
You've driven all the way here from Plymouth, Jason.
That's it, so I passed a few.
A lot of cameras on that road. I hope you haven't been caught today. Have you been snapped?
I actually once got flashed, but presumably the film had run out. I never got the fine through, so I was lucky on that one.
Hello, police. Phil's in the studio if you want to come get him. He just confessed live on the radio that he's actually been speeding. We presume he's been speeding anyway.
You can't prove anything.
The thing is that you can get round speed traps if you have a radar detector, because the way they work is they send out this barrage of waves, radio waves, which bounce off your car and then come back to the detector, and they exploit something called the Doppler effect. And in other words, this is the sound of how the sound of a moving object changes as it comes towards you and then goes away from you. You know how if you're listening to an ambulance or something, the siren sounds different when it's in the distance coming towards you as it does when it's going away. Thing is, because you can detect those radio waves with a radar detector, you can very easily find out where the speed traps are, and then you slow down just in time before they have a chance to nab you. Well, the police have thought of this, and in America, at the University of Tennessee, and also at the Patel Institute at Oak Ridge, they've come up with what they think's a way around this problem. They have invented something that uses nothing more than the sound your car makes to catch you when you're speeding. Now, what their device does is to position a tiny microphone that just listens beside the road to the sound made by your car's engine. And in exactly the same way as a standard speed trap works, as the car comes towards it and then goes away from it, it can tell, based on how the wavelength, the sound that the car engine's making is changing, how fast you must be travelling. And it can work out, therefore, whether you're speeding or not. But it's more clever than that, because this can also work out whether or not your car or lorry is overloaded, because it can listen to the engine, work out how fast the engine's turning over, and then as the car goes up a hill, for example, or the lorry's going up a hill, the engine obviously has to develop more power, so it speeds up. And by comparing how fast the car's going to how fast the engine's going, you can work out whether or not something is performing as you would expect it to, and therefore whether or not it's performing because it's overloaded. In 32 out of 33 trials of this technology, they found that they got the speed absolutely spot on to within a few percent. So if you are a speeder, then watch out, because the police could be rubbing their hands together and filling their wallets at your expense pretty soon. Phil?
I've got a story here, actually, how you can send stuff to space for less than a train fare. Now, a Californian company, Masten Space Systems, is offering a brand new service where you can send stuff into space and back for the cut price at the moment of just $99. That's about £55. And that's actually less than if I go up to visit my parents in Yorkshire from down in Milton Keynes. I pay over £60 for a train fare, so that's less than my train fare home.
But it is only a Coke can size of stuff, though, isn't it?
It is. You can't send just anything, actually. It's got to fit inside something about the same size as a pop can. It's got to be less than 350 grams as well. But you can send pretty much anything.
Not a bomb, though, Phil.
No, closer I think. There are a few issues. You can't send anything radioactive, nothing that's going to explode. You can actually send living things up there, though, so long as there are no animal welfare issues. So maybe leave the gerbil at home and not bother sending that. But they are thinking that they could use this sort of biology experiments, things like that.
Does it have a return to sender activity then? Do they send it back to you afterwards?
They do, yeah, absolutely. It goes up. It goes up to over 100 kilometres.
Yep.
A little pod opens, essentially. You can have... you get a few minutes of weightlessness or microgravity, and you can actually expose the inside of the canister to the vacuum of space if you want as well, or not, depending on exactly what you're sending up there.
Yep.
But you can really send anything you want. They think maybe school science experiments. You could even send grandma's ashes up there if you really want to.
And who is that again? Who's doing that?
That's Maston Space Systems. So get on the website and get something ordered.
Send something into space. It's the Naked Scientists, Chris and Phil, and if you'd like to ask us any questions, lines are open 08459 25 2000, or send me an email, chris@nakedscientist.com.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
Time now for Kitchen Science, and this is where we want you to get scientific, interactive and experimental and join in on the programme and do a bit of science in your very own kitchen. We're going to show you how a submarine works and how to make your own one. Derek's out with Sheena and Amanda, and they're in Essex at Colchester County High School. Derek, what are you up to this week?
Hello and welcome to Colchester County High School. This is where we've come this evening. Very warm welcome to you. And with me is a scientist who's new to the Kitchen Science feature and who's going to be doing a great experiment with us today, which you can do at home. So please do listen out for all the details. It's very, very easy. So, yes, could I get you to introduce yourself? Please tell me who you are and what you do.
Yeah, my name's Sheena Elliott and I'm a PhD student in Cambridge studying physics.
OK, then, and just quickly, what have we got set up? What are we going to be looking at today in the Kitchen Science?
We've got a Cartesian diver, and what we're going to be trying to do is simulate how a submarine works in a lemonade bottle.
Fantastic. OK, that is all coming up. And also, we've got a helper with us who's from Colchester County High School. So would you care to tell me your name and what year you're in, please?
My name's Amanda Talhad and I'm in Upper Six.
Excellent. Thanks for coming along. And we love to know, all our volunteers, kind of what they do in science and whether they like science. So are you doing science at school?
I'm doing all three sciences and maths.
Oh, right. Oh, OK. So are you going to kind of carry on and do more of that?
Yes.
OK, we already have a convert, but hopefully we'll be kind of switching you on science even more. OK, right then. So to do this experiment at home, let me just run through what you need. They're very, very simple things, and hopefully you do have them. So firstly, a straw or a pen lid. So some kind of drinking straw or the lid of, say, a biro will work very well. Secondly, you need a lemonade bottle. Now, the bigger the better, basically. If it's as big as 2 litres, that's very, very good. And it does need to be empty and filled up with water. And the third thing is some blue tack or plasticine. And that is it, basically. So Sheena is now going to tell us exactly what we do with these things and how to set it up.
OK, so to begin with, we need to take either a drinking straw, which we might cut up into, say, 2 centimetres or 3 centimetres long, or if not, we use our pen lid. And then we need to block up the ends. So if it's a pen with 2 ends or just with 1 end, we need to block it up so we just have an air pocket inside it. And the same with the drinking straw, you just block up both ends. So what you really want to have is an air pocket enclosed within the drinking straw with a pen lid. And it has to be a very good seal, so work hard to make sure that you get a really good seal. You then need to make sure that it floats, but you have to have it so it's only just floating. So practice in a mug of water or something. Put it into the top of the water. If it floats too high, then just add a little bit more plasticine or blue tack. If it sinks right down to the bottom, then you might have to take some out and play around with it so you get it just right.
OK, so the plasticine is kind of weighing it down, so you've just got to have the right amount.
Yep, that's right.
OK, and then what do you do with the lemonade bottle?
So then you want to fill your lemonade bottle right to the very top, so really to the very brim, so you've got no air at the top. And then you want to put in your little pocket of air, which is your straw or your pen lid, and just put that in top. And then tighten up the lid on the bottle of lemonade or a bottle of water and tighten the lid quite hard.
OK, so that's all the setup. Then what do people do?
Then all you have to do at home is squeeze the bottle and just squeeze it and see what happens.
OK, so there it is then. What you've got to do is get that kind of air pocket all set up. It could be a bit of straw about 1 inch long or a pen lid. Plug it at both ends with a piece of plasticine or blue tack and get the right amount of plasticine or blue tack so that it just about floats. And then get a full lemonade bottle, fill it up right up to the top with water, and put the little air pocket thing in the top and then put the lid on, screw it tight and squeeze the bottle and see what happens. So, of course, you can do this at home. We are going to be doing it later on in the show. Of course, we have a volunteer who's actually going to be doing it. And I wonder what, Amanda, do you think is actually going to happen when we've done this setup, when we squeeze this bottle with a little air pocket inside?
I don't really know, but I think it's going to rise.
It's going to rise. OK, then. Very good. Any reason? Why do you think that might happen?
I don't know.
OK, that's fair enough. Well, all will be explained later, because Sheena is also going to be telling us how this relates to real-world things that we do see around us. So that's great. Anyway, you at home, we want you to do this as well. I hope you've got all the details there now. We've been through them. Please do go and do this in your kitchen, and if you like, please call us with the result, because there are prizes to be won from the Naked Scientist. So the number to call is 08459 25 2000. You can also email chris@thenakedscientist.com. So we'd love to hear from you there. So until later in the show, we will be waiting poised next to this air pocket inside our lemonade bottle to see what happens. So do come back to us later to Colchester County High School. Goodbye till then.
Thanks, Derek. It's Chris and Phil here as the Naked Scientists, and if you'd like to ask us any questions, 08459 25 2000 is the phone number, or you can email chris@nakedscientist.com. Remember, we have in the studio Ron Douglas and Jason Hall-Spencer, and we'll also be talking to David Klein later on the phone, and we're discussing what's underneath the surface of the ocean, what's lurking in the deep, how deep are the oceans, what's down there. They're going to unlock all of that for you. Just join in on the conversation if you want to, 08459 25 2000. And if you do have any other questions, general questions for right now, to just send them to me by email as well, chris@nakedscientist.com. Got to say a quick hello to Nathaniel Kang, who's listening to us in Malaysia, also to Sakchar Uung Amluan, who's in Thailand. He says Sawasti, hello from Thailand, thank you very much. And also in Thailand is Dr. Sven Ivar Lawrenson, and he's actually not Thai, as the name probably suggests, but he is a scientist working on HIV and AIDS, and says he likes to listen to the Naked Scientist while he's on his way home from work on the Sky train in the evening. He said it regularly puts a silly grin on my face and probably makes my Thai fellow citizens think I'm another crazy Farang or foreigner.
The Naked Scientists. Supported by the Wellcome Trust.
The Naked Scientists, Chris and Phil, and if you have any questions for us, 08459 25 2000, or email chris@nakedscientist.com, as Shane McCarthy has done. Shane says, "Hi Chris, got a quick question for you. Why are some planets surrounded by rings and not encased by a sphere of debris? Shouldn't gravitational pull act in all directions? Maybe there's a simple answer to all this, I'm not sure. Love the show, by the way." Shane, Phil, what do you reckon?
Well, if you take, say, Saturn with its rings, now, Saturn is not actually a perfect sphere, because it's spinning. Sort of the mass gets thrown outwards, and it's actually a bit wider than it is tall. Now, because of this,
a bit fatter in the middle, sort of thing.
Yeah, a bit fatter in the middle. So, because of this, there's an actual concentration of mass round the centre, which means that stuff's more attracted to, like, the area in Saturn's equator rather than to everywhere else. So, even if you actually start off with a spherical sort of sphere of debris around Saturn,
cloak of mass,
around sort of Saturn, then eventually, as they sort of bump into each other and jostle each other and rub against each other, it'll all settle down into a ring, because this extra mass around the equator gives just that extra bit of pull to all the matter and form these rings rather than a sphere.
Which is exactly why all the planets in the solar system form the planar structures that they do.
Absolutely, and why moons tend to be in the equatorial plane of all the planets as well. All the same sort of theory.
OK, now here's good news for people that are worried about the Earth's dwindling oil supplies. In fact, we know that people are very worried about how much oil there might be left on Earth, and oil has now reached record prices. It's just going upwards and upwards and upwards. How are we going to deal with the problem? Well, there's a scientist called Alan Goldman, who's at Rutgers University in New Jersey, who's come up with something very useful, a pair of catalysts that can turn what are currently deemed as waste products from refineries into useful-length hydrocarbons that could be used in things like diesel fuels. Now, the way it works is that you can extract from coal, tar sand, and also the product of catalytic cracking, in other words, making refined fuel in a refinery. So very short-chain hydrocarbons, literally very short units of carbon and hydrogen joined together, and they're not terrifically useful. You can burn them, and that's just about it. Not terribly good as fuels, because you can't compress them easily into liquids that then can run like diesel can. This catalyst does a very clever thing. It takes a couple of these short-chain hydrocarbons and it rips a couple of hydrogen atoms off of them, introducing what's called a double bond between a couple of the carbon atoms. And then the second catalyst, which it passes them to, takes two of those and sticks them together end to end. And so you extend the chain, you make much longer hydrocarbons by gluing the two together. This is a process called alkane metathesis. And because you are linking lots and lots of little ones together, you can make bigger, longer chains, and you end up with things which are about 10 carbon atoms in length, up to as long as 18 carbon atoms in length, and this is perfect for making things like diesel fuel. And good news for anyone in America is that the US has enough coal to be equivalent to the total world's petrol supplies as it stands at the moment. moment if they use this technology. So it looks like you'll be able to carry on in your cars for at least the foreseeable future.
Okay, I've got a story here about Mars, actually. The Mars Express spacecraft's been in orbit now around Mars for a good time. It's just come up with some new results. They're actually using infrared light to look at the minerals on the surface, all the way out from orbit. Now, what they've found is that there were certain type of minerals, mineral clays, are found on Mars, and they were formed only in the first 500 million years of Mars's history. So Mars is 4.2 or 4.5 billion years old. Only in the first half a billion years were these clays formed, and you actually need water to form these clays. So that kind of shows that Mars did have water on its surface, but only for about 500 million years. Now, what they found on top of that layer of clays was a layer of sulfate minerals. Now, these were actually formed, I think, by an intense amount of volcanic activity that erupted on Mars, because as Mars sort of started to, or as Mars had been sort of formed for about 500 million years, it started to heat up by radioactivity, actually, from rocks inside Mars, which melted the internals, created a magnetic field, but also created all these volcanoes, which threw out all sorts of gases, including sulfur dioxide, which formed acid rain, which in turn then formed these sulfate minerals. Now, by this time, Mars is looking pretty nasty place, especially if you're some sort of bacteria wanting to live on Mars. By this time, it's looking pretty nasty. Now, after 500 million years of this, Mars actually started to cool down. The magnetic field was stopped, the volcanism stopped, and because there was no magnetic field, it allowed gas blown out from the sun just to blast Mars's atmosphere away, if it had an atmosphere at the time. And basically, you were left with a barren desert. And that whole thing then has been sat now, Mars, rusting away. The red colour of Mars is actually caused by iron in the rocks, rusting. And Mars has now been a barren desert for, well, 3.5 billion years. So, although it's looking pretty poor for any prospects of life on Mars, what it does mean is that we know now where we want to look. If we're going to look for life on Mars, we want to look in these sort of silt beds that they found on Mars. That's where we know there definitely was water at one point. So maybe life, maybe not. Still an unanswered question.
Now, one thing that people are very interested in doing is getting into a place called Lake Vostok, which is essentially a time capsule, or so we thought. It's a subglacial lake. It's a lake of water which is sealed inside the ice of Antarctica, and it's one of many, actually. And people think that it contains water that's been there for a very long time and might have a unique ecosystem. Life might be living there and has evolved independently of other forms of life on Earth, at least for a long period of time, which means there might be some interesting things in there. But then someone came along called Martin Siegert from the University of Bristol this week, and he's really stirred up a heap of trouble because he's found, by looking from space, that actually these lakes might have something that they didn't tell us before, which is that they're all in communication with each other and huge amounts of water are moving around, which we didn't know before.
Deep underneath the 4 kilometres worth of the Antarctic ice sheet, we've discovered that a subglacial lake has lost rapidly a large part of its volume, and this water has moved over 200 kilometres into another subglacial lake.
How did you actually do it, though? How do you know that water's moved around?
Well, we looked at how the ice sheet surface changes, and we had a satellite that was looking at the changes in ice sheet surface elevations, and we noticed that one part of the Antarctic ice sheet lowered by 3 to 4 metres over a course of a year, and 200 kilometres away, the ice sheet surface elevation went up by about a metre. That's a very unusual change, and there were very few alternative explanations for that amount of surface change, in fact. And actually, losing that amount of mass from the surface of the centre of East Antarctica, which is a very stable ice mass, it can only be the removal of something really rapid, and all the alternatives point to being water.
Do you know what's driving that movement of water, though? What's pushing it along?
Indeed. Well, the base of the East Antarctic ice sheet, much of it, is at the pressure melting point. So there's water being melted from the underside of the ice sheet, and all this water will feed down into subglacial lakes where it collects. The subglacial lakes will be pressurising because water will be coming into them, and the ice sheet will be attempting to hold that back. And so that's an unstable situation. The ice sheet can't hold it back forever, and as the pressure increases to a threshold, the water will escape, and so it sort of outbursts.
People are quite interested in those lakes, aren't they, for the simple reason that they're viewed as time capsules in the case of Vostok and similar bodies. Your work must therefore have those people quite worried.
Well, I don't know about that. It's actually only been 10 years ago since a paper was published in Nature on Lake Vostok, and really since then people were talking about these lakes as being very isolated, distinct systems. systems. And actually what we're identifying now is that maybe that's not the case and that'll have to be revised. But it's still very exciting from a subglacial exploration point of view. I don't think it would harm the chances of going into subglacial lakes or even belittle the types of science that could take place in those systems.
The escape of so much water all at once, does that have any other consequences in terms of, say, salinity of the surrounding ocean, animal life, that kind of thing?
Well, I mean, we haven't shown that this water can get to the ice sheet margin, but even if it did, it is quite a large amount of water. It's 1.8 cubic kilometres worth of water that we've seen transferred, but actually that's a very small amount in terms of global ocean values, and so it wouldn't have too much effect.
Do you think climate change is having any kind of implication or bearing on what's happening here?
Well, I don't think so. The situation that we have is the underside of the Antarctic ice sheet. And remember, this is the East Antarctic ice sheet, which is the stable part of Antarctica, and there really isn't very much change going on there. What we think we've seen is a process which is common both now and in the past. It's just the first time that anyone's actually seen it.
And what questions are you now gagging to answer on the basis of the intriguing observation you got here?
Well, what we'd like to do is to find more of these processes, both in East Antarctica and in West Antarctica, because we know that a subglacial lake has lost mass and that water has flown underneath the ice sheet and into another lake. What we now have to try and do is understand the physics of the problem a bit better, and that will require us to get more data, more observations in order to constrain the system better than we have done up until now.
That was Martin Siegert from Bristol University talking about how a shake-up in the South Pole may be making the ecosystems under the ice much more worth a look. It's The Naked Scientists, Chris and Phil, and we're joined this evening by Ron Douglas and Jason Hall-Spencer, and we're going to be talking about the deep oceans. If you have any questions for us relevant to that subject, 08459 25 2000 is the phone number, or you can email chris@nakedscientist.com. And in a second we're going to be talking to John, who's in Ipswich, about lie detectors. Hi, John.
Hello.
What would you like to talk about?
I would like to know how anyone can tell whether I'm telling the truth. Exactly how does a lie detector work?
Have you got any nefarious activities in mind at the moment, then?
I have not, no.
Well,
I've seen them being used on TV programmes,
sure.
So I just wonder exactly how accurate they are and what happens.
The answer is not very, and the answer is you can get round it. It's called galvanic skin response, actually, and the way in which a lie detector works is it measures changes in skin conductance on the basis of sweating. And it uses the fact that usually when you're telling a porky, a lie, your skin goes up in terms of its conductivity because you sweat, and you sweat because you're nervous. And when
you blush, then can do.
Exactly. And it's really interesting you should say that, because in fact there's another group of researchers who in the last few years have been looking at a different way of telling whether people are lying, which is studying closely the blood flow across the face. They've found that when people tell a lie, and this is going back a few years, and so I think it's probably still undergoing tests, but when people lie, the blood flow around the eyes specifically changes and you get increased blood flow, even though your eyes might not be sensitive enough to pick it up. A clever camera can, so you can look at the heat or the thermal changes in a face and you can tell whether someone might be trying to hide something. And they were thinking this would be useful, say, at the airport. If someone's checking in and they're asked, has anyone tampered with your baggage? Is there anything that you shouldn't be carrying that you might be? People might be very good at going, oh, no. And in fact, that they're lying. And this might be one way to flush them out without actually having to do anything invasive, i.e. strap on things to their body to tell whether they're telling the truth.
Well, with technology advancing as it is nowadays, anything's possible.
Do you want to have a quick go at the quiz, John? We have a wonderful book this week called Living Science. It's, in my opinion, the best science book, I think, to come out this year. It's published just newly by Oxford University Press, and it explains the science of everyday things beautifully clearly. We've got a copy to give away tonight if you win.
Right.
Do you want to have a go?
I'll have a go.
OK, the world's first manned space flight to Mars is due to blast off in June next year. Is that fact or fiction, John?
I think it's fiction. We've had one already, I'm sure. Oh, the manned flight? No, that's fact, I think.
Oh, well, you were right first time, so it's actually false, yes.
It's a man, yeah.
There are no plans at the moment to send anyone to Mars in the near future, at least.
Next one, the world's biggest flea is found in North America. It can reach 1 centimetre long. Fact or fiction, John?
I'll go for fact this time.
Absolutely right again. Bit of a tongue twister. Hystricopsilla schefferi is the world's largest flea, lives in the fur of North American mountain beavers.
If you can say that word again, John, I'll give you a bonus prize.
No, I don't think I'll try.
Okay, last question. Bulls are attracted by the red colour of a matador's cape. Is that science fact or science fiction?
Well, I've heard that said so often that I think I'll say it's fact. Oh.
Unfortunately not. Bulls are actually colourblind, so they can't tell what colour it is. They're attracted by the movement instead, not the colour.
Ron was going to add something. Go on, Ron.
I don't like to contradict one of the presenters, but bulls are certainly not colourblind. Bulls are dichromats, which means they have two types of cones, so they see the world like a red-green colourblind person, and they can certainly see the red.
But are they interpreting it as red? I think that's what Phil's getting at.
Yes, I think they are. They are interpreting it as red, but they are not attracted to the red colour. Yep. It's more the movement of the cape.
It's more the fact that they're being wound up by something which is easy for them to catch sight of.
It could be a lime green cape with pink dots on it. It's just that the matador probably wouldn't like to strut his stuff with a lime green cape.
Thanks, Ron. Thank you very much, John.
Cheers. If they saw me, they'd run the opposite direction anyhow, I reckon.
Well done. 2 out of 3 on fact or fiction. It's the Naked Scientists, Chris and Phil, and if you have a science question for us, 08459 25 2000, or you can email me, chris@nakedscientist.com. You heard there Ron Douglas. We'll be talking to him very, very shortly. He's from City University in London, and he explores the deep ocean, and we'll also be talking to Dr. Jason Hall-Spencer from the University of Plymouth, who is interested in a similar sort of thing, and corals and the impact of fishing.
Sorting out the sparks from the quarks. The Naked Scientists.
The Naked Scientists, Chris and Phil, and we're here with you for about another half an hour, and we're talking now about the science of the deep oceans. A couple of quick emails. Martin Waters is in Suffolk, I presume, from his email address, and he says, "Hey there, are you naked? Haha. Yep, well, if you check out the webcam, Martin, you'll see, genuinely, yes, we're all stripping off here and laying the facts bare for you live on the radio." Also got a quick question. Simon's in Braintree. He's had a go at kitchen science. Let me remind you, this evening we're trying to encourage you to find out in your kitchen how a submarine works. All you need to do is get a lemonade bottle or something similar, fill it with water, then you take a piece of drinking straw about 2 or 3 centimetres long, an inch in the old money, seal up the ends with plasticine, make sure you get a good seal on the end, plasticines or blue tack, and you need it so it just floats in the bottle. Drop it into the bottle, put the cap on, screw it up tight, and then squeeze the bottle. What happens? Simon says he thinks that when you squeeze the bottle, this is called a Cartesian diver. He thinks it will rise, and then when you let the bottle go, it will sink again. What do you think at home? There's a prize to be won. We have a copy of Living Science, one of the best science books to come out this year. Got a copy to give away this evening on The Naked Scientists. It could be yours. So get calling now, or get experimenting now. 08459 25 2000, or you can email me, chris@nakedscientist.com.
Laying the facts bare. The Naked Scientists.
Well, now we're going to find out about Venus Express that entered orbit around Earth's closest neighbour about 2 weeks ago. The European Space Agency spacecraft will investigate the atmosphere and surface of Venus. Daniel Skuka from the European Space Agency was in the main control room as this crucial manoeuvre was completed. He spoke to some of the key players to find out their reactions.
This past Tuesday, April 11th, engineers and scientists from the European Space Agency crowded into the dimly lit main control room at ESOC, ESA's Space Operations Center in Germany, to monitor the entry of Venus Express into orbit around the hothouse planet. Positive confirmation that the spacecraft had successfully fired its main engine to slow into orbit came at 11:12 a.m. Central European Summer Time, when ESOC mission controllers re-established the radiotelemetry link with Venus Express after a series of critical and complex maneuvers. The dramatic activity began just after 8 a.m. when Venus Express automatically swung itself into a slew maneuver to point its main engine in the direction of travel. After firing its smaller thrusters, the main engine fired for 50 minutes, reducing the spacecraft's velocity so that Venus's gravity could pull it down into the first capture orbit. You could literally feel the tension in ESOC's main control room as the spacecraft dropped behind Venus at 9:45 a.m. as scheduled, causing a communications blackout. Venus actually blocked the line-of-sight path between the spacecraft and Earth. For a very long 12 minutes, radio contact was not available. Low-bandwidth radio contact was re-established at 9:55 a.m. as Venus Express emerged from behind Venus, and full telemetry was back just over an hour later. Immediately after the spacecraft signal had been reacquired, I spoke with project manager Don McCoy in ESOC's main control room.
went absolutely nominally. So in that sense, it's been an excellent mission. And given that sometimes machines don't work the way you want them to, that's a surprise. But it was very nominal. It's an indication that the satellite was well built, well tested. The crews of people here are working absolutely correctly, and so the whole thing has worked very well.
I also spoke with the engineer most responsible for making the maneuver a success, Flight Director Manfred Vorhout.
Yeah, I think it's outstanding what has been delivered here by a joint effort from industry, from ASTEC and ESOC, and I do not want to address anybody in particular. I may say a few words about the navigators, because they made sure that we really arrive at Venus in the proper corridor, and finally we did it, yeah, and I'm more than happy, I tell you. Yeah.
Venus Express mission controllers now enter an intensive orbit entry period with additional engine firings and maneuvers designed to lower the spacecraft into the final 24-hour operational orbit. Scientists will then have to wait until June 4th for the spacecraft and its instruments to be commissioned and verified and to kick off formal science operations around the hothouse planet. Venus Express is ESA's first mission to Venus and the first mission at all since 1994. For the European Space Agency, I'm Daniel Skuka, reporting from the European Space Operations Center in Darmstadt, Germany.
Daniel Skuka, who was there for the crucial orbit insertion on the 11th of April.
So, Phil, what else are they going to be looking at when the mission's established itself? What sorts of things will they be investigating?
Well, Venus is really an interesting place, and somewhere we haven't really been to very much. It's covered in a surface of clouds, so we really can't see straight down to the surface. Now, there were missions previously that actually landed on the surface, but because Venus is covered with a really nasty acid rain, it's an intense atmospheric pressure down on the surface. The missions actually didn't last very long, so we didn't get huge amounts of data from them. We've also had orbiters go in and actually do radar maps of the surface, try and get the altitude of the surface. But this mission is really going to increase our knowledge about what's going on sort of on the surface and in the atmosphere of Venus. It's going to be really quite an interesting mission to watch out for.
Now, one of the people we have with us this evening is from the University of Plymouth, Jason Hall-Spencer. Good evening, Jason.
Hello there. Yeah.
Tell us about your research, because you're looking at corals principally, aren't you?
Yes, but I'm looking at deep sea corals, and previously people thought that corals only occurred in the tropics, making great big coral reefs, but we've just been discovering some really huge ones off the coastline of the UK.
I think probably, and I'm probably included in this, a lot of people are thinking, well, what actually is coral?
OK, well, it's related to an anemone, but it's got a hard skeleton, like we've got a hard, chalky skeleton inside of us. These corals have got a hard, chalky skeleton too. But what's peculiar about them is they've got stinging cells. They're like harpoons that inject their prey, and that's what they use to catch their prey.
But when you see this big chunk of coral reef, is all of that one massive alive organism, or is this like an ant's nest with lots of little ants that all cooperate to make one big colony home for themselves?
It's more like an ant's nest, I suppose, because each individual polyp, these are the individual anemones that make up the reef, form a great big skeleton together. They're called sort of ecosystem engineers because they form these great big reefs that capture their prey.
And how big is each of those polyps then?
Well, each one of the reefs I'm studying, each polyp's about the size of your thumbnail, actually. But if you're the size of their prey, a little tiny flea-sized organism, that's a large mouth ready to catch you and rip your head off.
So they're pretty big.
Yeah.
Now, how did they evolve? What was their origins? Where do we think these polyps came from?
We think they came from things like Hydra, which they've got lots of tentacles, they've all got stinging cells, and they're all related to things like jellyfish. Okay, and these are sedentary jellyfish that live on the bottom and then form a skeleton.
So why is it significant that some live deep and some are shallow dwelling animals?
Well, we didn't actually think that large reefs were formed in deep water. We thought that they had to be living in shallow water where they can capture enough light to feed their symbiotic algae that live in their skeletons. But it turns out that we've just been able to discover some large reefs in the deep waters off Ireland and Scotland and Norway. And that's very significant because you think people know the deep sea quite well, but actually there's large reefs there that no one knew about until 5 years ago.
Tell us a bit about that symbiotic relationship. In other words, two organisms living side by side to their mutual benefit. Tell us a bit about how that relates to these algae and things like that.
Well, symbiosis is where two different unrelated organisms benefit each other. Okay, so in the case of the corals in the tropics, there's an algae that lives inside its tissues that captures light and makes sugars, and that benefits the corals themselves, but then the corals benefit the algae by being a very highly armoured vehicle in which they can live.
Is it just a protection thing, or does the coral do anything else for the algae?
The coral provides the algae with its waste products, which are nitrogenous, which the algae would otherwise find very difficult to get hold of.
Because algae are tiny plants, aren't they?
Yeah.
And when you go deep down in the ocean, I mean, what sort of depths are your corals that you're talking about growing at?
The ones typically the ones I'm looking at are a kilometre down. Okay,
that's a long way. I mean, how much light is there down there?
There's no light, and we lowered some polystyrene cups down to that depth, and they're crushed down to the size of a thimble, so it's huge pressures. Yeah. So
how does the coral stand that kind of pressure?
Well, because they don't have any air pockets within them. We've got air pockets in us, and so's a polystyrene cup. If I was lowered down on a rope down to a kilometre depth, I'd implode. My skull would be crushed because I've got sinuses in there that are air pockets. But because there's no air pockets in a coral, it can withstand any depth.
And so if there's no light, if they can't use light, they can't have these algae, how are they getting their energy? How are they metabolising?
Well, the jury's still out on that, actually. Some people think that, lots of geologists think it's because they get their energy from methane seeps or from hydrocarbons that are coming out of the seabed. But actually, I'm of the opinion that it's because they live at depths where plankton that settles down from the surface of the water is concentrated into a thick soup, and that benefits the corals at depth.
A lot of people say that there are some interesting things lurking in the ocean depths that might benefit mankind in terms of medicine, that kind of thing. Are there any examples from these deep water corals that you can think of, or whether that might be relevant?
No, there's an intensive search on. The French are particularly looking for chemicals that can help with cancer in sponges that live in the deep water. But to my knowledge, we haven't discovered that yet.
So why are these corals important?
Well, they form habitats that are very important for the breeding and feeding and daily lives of fish. And they form part of the life history of these deep-sea fish populations. They hang out on these corals. And unfortunately, these corals are very, very easily damaged if you tow fishing nets through them. So the fish are attracted to the corals to feed and breed, but they also make the corals vulnerable to fishing equipment, unfortunately.
It's pretty deep, though, a kilometre. What sort of fish are knocking around a kilometre down?
There's all sorts. They've got unpleasant names. There's things like black scabbard fish or pudgy cuskeel, and they're things that, if you put on your plate, they look a bit revolting. But what people do is they fillet them and then put them into school dinners in France, for example. And so
just in France?
Well, no. Well, there's some of the fish are very attractive. Like there's the orange ruffy, which graces the tables of the finest restaurants in London.
Yep.
But there's others that are a little bit less appealing, but yet the flesh is good to eat. So they form fillets, and you wouldn't know if you bought this fillet fish that it was necessarily a deep sea fish.
Where are these reefs principally located? Around the coast of the UK and that kind of thing?
Yeah, well, it seems, and we don't really know because we haven't looked at a lot of the seabed at depth in the Atlantic, for example, but it seems as if they're concentrated in areas where the seabed was glaciated in the past. So where, for example, icebergs trundled down the coastline of Europe, they scarred the seabed with deep trenches and left behind lots of piles of stones that are scraped off the mountains. And it seems that these piles of stones are in the way of strong ocean currents that provide these corals with A, a substrate to live on, and B, the food that they need to survive.
Are they threatened, then, by the fact that we're just non-discriminately going out there with massive great nets and essentially ploughing the seabed?
Unfortunately, yes, highly threatened at the moment because we've got to a stage where some of the shallow water fish, for example, cod, are much less abundant than they were in the past. So people are becoming desperate in a way, looking deeper and deeper to catch deeper fish populations. And this is the frontier of new exploration. Areas that haven't been touched since the last ice age are now being trawled through with heavy trawling gear.
So, Naked Scientists, and you're listening here to Jason Hall-Spencer, who was talking about deep-water corals. We'll be joining David Klein from the Smithsonian Tropical Research Institute, who's in Panama very, very shortly. If you have a question or you'd like to join in the discussion, 08459 25 2000 is our phone number, or you can email chris@nakedscientist.com.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
Right, let's have a quick chat to David. Hello, David.
Hi, Chris.
Thank you for joining us. Tell us about your research and what specifically you're looking at in relation to coral.
So basically, I work at the Smithsonian Tropical Research Institute in Panama, and I've been studying how tropical reefs have been declining. So throughout the world, reefs have been declining at a really scary rate. It's been estimated that 20% of the world's reefs have already been effectively destroyed, and an additional 50% are under a long-term threat of collapse. And the situation is even worse in the Caribbean. And I basically have been looking at how all the different types of pollutants that we throw into the ocean, how they change the relationship between the corals and their symbionts. But besides just the algal symbionts, I'm also looking at bacteria that live in the coral tissue and how the pollutants affect these bacteria and potentially lead to diseases and mortality of the corals.
So those bacteria are bad for the coral?
Well, actually, just like the plants or the algae that live in the corals, when they're in controlled levels, they're actually quite good for the corals, and the corals are dependent on them. These bacteria can protect the corals from harmful bacteria, other harmful bacteria. They can provide them with vitamins and other limited nutrients that they wouldn't be able to attain otherwise. So under normal, healthy conditions, these bacteria are actually quite important to the health of the corals.
So when you chuck in a nice healthy dose of pollution, what's the impact on the coral then?
So what happens then is, so the main components of pollution that people monitor and that are monitored on reefs are nitrates and phosphates. And these don't actually affect the corals or their bacteria directly. But what is a component of pollution that affects the bacteria are simple sugars. There's high levels of simple sugars associated with sewage and also with runoff associated with agriculture. And these sugars just are the perfect food for these bacteria. And the bacteria can basically grow so fast that they overwhelm the coral, causing disease and mortality. So
and there must be knock-on effects there, David, for because Jason was talking about the fact that his reefs play home to a huge variety of fish, and that's obviously in the deep water, but that must also be true in the shallows.
Yeah, that's very true. The coral reefs in the tropics are a nursery for a lot of the commercial species that we eat. They're the home of many invertebrates that we eat, such as lobster and conch. And when the corals start to die, you lose a lot of the biodiversity associated with them that includes these fish and other animals that we eat.
The key question that's going to be going through a lot of people's minds now has to be, is it too late, or can we actually remedy this?
I'm more on the optimistic side of this debate, but I think there's a lot of things we can do. There are things such as sewage treatment that definitely can be improved. In the Caribbean, less than 10% of the sewage is treated before being released onto the reefs. So sewage treatment is a big thing that we can do. There's marine reserves that are being set up that can help bring back the fish and reduce fishing pressures on reefs. And it's been shown that marine reserves can actually have really big impacts on improving the health of reefs. And we can also reduce CO2 emissions, try to use more fuel-efficient cars, and try to drive less, because with CO2 emissions, we get global warming. And with global warming, as the oceans heat up, they can disrupt a lot of these symbiotic relationships, leading to things like the bleaching events that we've been seeing all around the world.
David, thank you ever so much for joining us and highlighting the plight of corals in tropical waters.
Thank you very much, Chris.
David Klein, who's at the Smithsonian Tropical Research Institute in Panama. We're going to talk next to Dr. Ron Douglas, who's from City University in London. If you'd like to ask us any questions about the deep oceans or the shallow oceans, it's 08459 25 2000, or you can email chris@nakedscientist.com. Jean in Cambridge wanted to know what is global dimming. The simple answer to that, Jean, is that when you put particles into the air, and a common culprit are cars, our activities, industry, but a very, very big culprit are volcanoes. When those particles go up into the atmosphere, they can reflect the sunlight back out into space. They stop it coming through into the atmosphere, and of course the sun is the key source of warming and energy input to our planet. And so actually, in real terms, when you have a big volcano, despite the fact it releases an enormous amount of heat, it releases enormous amounts of ash, and that correspondingly then cools the planet. Most people think volcanoes might heat the place up. They actually cool the planet down for quite some time, and a recent piece of research in the journal Nature showed that Krakatoa, that blew up off Indonesia over 100 years ago, still has a legacy living on in the oceans today. In fact, over 100 years later, you can still see a big body of cold water and a lower sea level because of that. So Naked Scientists, Chris and Phil, and if you have any questions for us, now's the time to call 08459 25 2000. very, very shortly we'll be hearing from Archie. Now, Archie is a giant squid that's down at the Natural History Museum, and Fran Beckerleg, who's our roving reporter, has been down there to introduce herself to Archie. But before then, someone who's from not so deep in the ocean, but nonetheless goes there occasionally, Ron Douglas. Hello, Ron.
Hello.
Thank you for joining us. Tell us about your research.
I'm interested in knowing what animals are down there and what it is they do. The problem is that it's very difficult to actually make observations on living animals in the deep ocean. You have two ways of catching animals. Mainly I'm interested in fish. You can either send down nets. Now, it's very difficult to actually fish for things using nets because they're the size of a football goal. And if you say the average depth of the ocean is 4,000 metres, if you want to fish from 4,000 metres, you actually have to let out about 15 kilometres of cable. Now that takes maybe 12 hours to get down and to get up. And what you end up with is perhaps a bucket full of organisms, most of which are dead. The alternative is to actually go down in a submersible. But a submersible also has problems because it's noisy, it has lights, and you're going to scare things away. It's rather akin to, if you want to look at lion behaviour, going into the veldt in perhaps a Land Rover at night with the lights flashing and the stereo on full blast, and you're not actually going to see meaningful behaviour. So really all we see in the deep sea with submersibles is the dumb, the deaf, and the stupid, and the dead.
Can we define first what deep sea is? Because Jason said he's been plumbing the depths at 1 kilometre. How deep is deep in your book, though?
The average depth of the ocean is 4,000 metres, but the deepest point is round about 11,000 metres. Deep sea is usually defined as that area below where photosynthesis can occur, which is about 200 metres.
And beyond that point, there's not enough light for anything to be meaningful?
There's not enough light for photosynthesis. Humans can perceive light if you go down in a submersible, switch off all the lights. You can see some light, some sunlight, down to about 700 or 800 metres. The animals that live there are a little bit more sensitive, and they can see sunlight down to about 1,000 metres. But the thing we must remember is that almost all animals, about 80-90% of animals in the deep sea, actually produce their own light. That is, they bioluminesce. So if you actually go into the deep ocean and you switch the lights off in the submersible, as the sunlight fades, it's replaced by a bewildering array of flashes. It's rather like being in a firework display, as all the animals are talking to each other and illuminating each other using their bioluminescence.
But some animals, because I mean, one thing that anyone that's gone underwater will notice is how blue-dominated the environment is, because am I right in saying that seawater, or any water, scatters and gets rid of red light, and only blue light comes down, so by the time you get very, very deep, you're in a blue world, and therefore the animals that are knocking around down there are optimised to see blue, but not reds.
Absolutely right. I mean, if you go diving even off the coast of Britain, if you cut yourself, you don't bleed red, you bleed this kind of alarming green gooey stuff, because all the long wavelengths, that is the red light, has been absorbed by the water. So as you go down the water column, after about 200-300 metres, all you're left with is blue light. And almost all of the animals down there have eyes that are only sensitive to blue, because that's the stuff that's transmitted furthest.
But what about these animals that have exploited that evolutionary niche and are now producing their own light, which is red, which means they're essentially able to focus a searchlight on all their prey, because their prey aren't sensitive to the red light, but the fish that's making it can see them beautifully?
That's right. I mean, most bioluminescence, as I've said, is blue, and almost all fish are therefore sensitive to blue. But there are 3 species of deep-sea fish which have the lovely name of dragonfish because of their large teeth and jaws, that are actually able to produce light, and they have eyes that are sensitive to that red light. And they can use this for a number of purposes. For instance, they can illuminate prey, and the prey won't know they're being looked at because they're not sensitive to the red light, so it's rather like a sniper scope in the army. And of course the other thing is that these animals can talk to each other without their potential predators knowing they're there. So if you like, it's a teenager's dream, as much sex as you like, and nobody actually knows that you're at it, because you can flash your red lights at each other and you're quite immune from detection by anybody else.
The statistic I said earlier was, 3/4 of the Earth's surface is covered with water. We know more about the surface of the Moon and Mars than we do about the deep sea. What about the deep oceans and the trenches, for example? They're, 7 kilometres down, aren't they, some of them? And when was the last time anyone went there? How do we know what's down there?
Well, I mean, first of all, the statistic you say that 3/4 of the Earth is covered in ocean is absolutely right. But what you have to realise is that life on land is really two-dimensional. Everything happens within a few metres of the ground. But as I said, the average depth of the ocean is 4,000 metres. So the volume of habitat available is absolutely enormous. And in fact, 99.9% of all available living space on the planet is deep ocean. And we know really incredibly little about it. To answer your question, only 2 people have ever been to the bottom of the ocean at 11,000 metres, Don Walsh and Picard, in 1960, and nobody has been back since.
Time now to head across the Atlantic and join the guys at Science Update, Chelsea Wald and Bob Hershon.
This week on Science Update, we'll be talking about fish. Many of the world's fish species have been overfished to a tiny fraction of their original numbers. And in order to help rebuild one population, scientists in Florida are undertaking an ambitious underwater surveillance program.
High-tech listening devices, surgically implanted transmitters, tracking thousands of subjects without their knowledge. Is it a controversial homeland security program? Well, maybe, but what we're talking about is a fish research project. University of Miami marine biologist Jerry Ault and his colleagues are implanting acoustic transmitters into thousands of Florida grouper in and around a marine reserve. Then they're re-releasing them and listening in with underwater microphones.
The transmitter itself is pinging about every 20 seconds or 3 times a minute. Each pinger has a unique acoustic code so we can identify individual fish.
By understanding how the grouper use the protected waters, the researchers hope to figure out how to replenish their overfished population while still keeping area fisheries well stocked.
Unfortunately, there are still some places that fishing nets can't reach. One of them is the abyssal plain, the ocean floor located about 4,000 meters under the surface. The total darkness and intense pressure there have made it a very challenging place for researchers to get to know.
Yes, scientists at Scripps Institution of Oceanography in La Jolla, California, have now taken the first long-term look at the abyssal plain, and what they found was surprising. The population of a fish called the grenadier tripled in 15 years. Marine biologist David Bailey says this boom is likely the result of natural ocean cycles, like El Niño, that affect the production of nutrients on the surface.
How productive the surface waters are strongly affect how much food arrives on the seafloor, which is what feeds the fish we're working on.
He says so far there's little sign of human influence on these fish populations, a rarity anywhere on the planet.
So let's hope it stays that way. For next week's Science Update, a riddle. What's brown, sounds like a bell, and can cure the energy crisis?
I don't know. What is brown, sounds like a bell, and can help cure the energy crisis?
Well, you'll just have to tune in next week to find out. Until then, I'm Chelsea Wald.
And I'm Bob Hershon for AAAS, the Science Society. Back to you, naked scientists.
That was Chelsea Wald and Bob Hershon from Science Update. More details on their website at www.scienceupdate.com.
Laying the facts bare, the naked scientists.
Right, time now to catch up with what Fran Beckerleg has been up to at the Natural History Museum this week, where she went and introduced herself to Archie, who's a giant squid.
Archie was actually caught by some fishermen who were fishing just off the coast of the Falkland Islands. When they actually caught it in their nets, they kind of realised what they'd got was so important. They took it to a research station who immediately realised it was too big for them to handle, so they donated it to us.
What's so special about this specimen?
Well, giant squid are very rarely known. Most of the specimens around the world either come from specimens that have been washed up onto the beach, in which case they're very badly damaged, so there's very little of them left, or they come from the stomachs of sperm whales, in which case they're very badly digested. So to have a specimen in such good condition, so complete, is really amazing, and it really is quite a large specimen.
And how did you go about preserving such an enormous animal?
Well, when it arrived at the museum, it was actually frozen, so the first thing we had to do was to defrost it. This was quite difficult because the mantle, which is the thick body, took a long time to defrost, whereas the arms and the tentacles defrosted very quickly, so it was kind of a vigorous regime of kind of keeping the tentacles frozen with ice packs while sort of hosing down the mantle area. Once the whole specimen was defrosted, that took about 3 days. We had to inject it with a preservative called formylsaline, and this is kind of a mixture between formaldehyde and salt water, and this stops it from rotting sort of from the inside out.
How far down in the sea do giant squid normally live?
Well, like a lot of things about giant squid, we're not really sure about the way they live. It was only actually at the end of last year they were sighted for the first time in the wild. 2 researchers from Japan actually filmed them. But sort of estimates by studying sort of specimens that have been found, and also from whales, which are sperm whales, which are the main predator, we think they probably live at a range of about 200 metres and 1,000 metres.
It must be pretty high pressure down there. Do they have any particular adaptations which allow them to live that deep?
Well, they actually fill the tissues of their skin with ammonia, which most squids would excrete, and that enables them to get neutral buoyancy in the deep waters. Also, they don't have that many areas that you can compress, unlike sort of fish, which may live at the surface, so they're quite stable animals.
And it must also be quite dark down there. How do they find their way around?
Well, giant squid actually have the largest eye of any animal. In this specimen, it's about 23 centimetres across. And lots of people ask me, well, why do they have such a big eye at such great depth? And again, we don't really know. But lots of animals down there actually bioluminescent, they produce flashes. So one thought is possibly they have this wide eye to capture some of the flashes that might occur deep down, and possibly they either want to avoid or to find to eat.
So do you know what kind of things giant squid eat?
Yeah, there's been quite good studies on the stomach contents of giant squid. They seem to eat a mixture of sort of fish, hoki and hake, slightly smaller squids, and there's even been reports that they may be cannibalistic, but we're not sure how true that is.
Is Archie a fully grown giant squid, or are there bigger giant squid than Archie?
Well, the biggest reported giant squid was about 18 metres, which is nearly double this size. That was caught in 1880 in Newfoundland. It was caught a long time ago, so it's not 100% sure how true that is, but giant squid tend to be around this size, with kind of the maximum average size being around 13 metres.
And what's going to happen to Archie now?
Well, hopefully she will be on public display forever, not only to the public but also to researchers. So if scientists from around the world want to come and study the specimen, then they'll be able to come here and visit it.
That was Fran Beckerleg, our roving naked scientist reporter, down at the Darwin Centre at the Natural History Museum in London, catching up with John Ablett to hear about the giant squid, Archie, that they have on display there if you want to go and see it.
Stripping down science.
OK, let's do it.
The Naked Scientists.
Earlier in today's show, we were asking you if you had any idea as to what would happen if you took a drinking straw, blocked the ends off with plasticine, shoved it in a lemonade bottle so it just floated, did the top up tight and squeezed it. What would happen? It's called a Cartesian diver, and Derek, Amanda and Sheena are at Colchester County High School doing exactly that experiment, and we invited you to have a go. And what's the answer, Derek?
Hello again. Welcome back to Colchester County High School, where we have been waiting for the last part of the show, just waiting to do the experiment with this lemonade bottle, which has got this kind of floating thing ready inside it. And Sheena's here as well. So, Sheena, would you care to instruct Amanda about what she's got to do now?
OK, so, Amanda, all you need to do is step towards the bottle, put your hands around it and just give it a little bit of a squeeze.
And please tell us what you see.
It's gone down.
OK, tell me more. What's gone down and how far has it gone?
It's gone all the way to the bottom.
OK, and then when you release your hands, what happens then as well?
It rises up again.
OK, so what we've seen then is when Amanda squeezed the bottle, the bit of straw with the plasticine on it in the air pocket inside has sank all the way to the bottom of the bottle. And then as soon as she took her hands away, released the pressure on the bottle, it just came back up to the top. So, Amanda, have you any idea why that's happened?
I have no idea.
OK, well, that's absolutely fine, because all will be explained, because, of course, Sheena Elliott is here, who set up this experiment. So, Sheena, what's happening here, firstly?
So before we can explain what's happening, we really need to understand why it floats. What's the difference between something that's floating and what's something that's sinking? So to this, we're going to turn to Archimedes' law. And what Archimedes said was that for something to float, then the amount of water that it displaces has to weigh more than the thing that you're trying to make float. So obviously, when we have our straw that's floating to begin with, it's obviously taking up more space of water, and that water weighs more than the straw, and it's sort of in ensemble with the plasticine. Therefore, it's floating.
OK, let's just imagine an example here. I mean, I'm imagining something very big and very light, like a big piece of polystyrene or something. I mean, I suppose that takes up much less weight of water, doesn't it, if you kind of put it on the water, and so it doesn't displace it and it doesn't sink.
Yeah, exactly. It's all down to density, because you're talking about the volume of what it takes up and how much it weighs. And so what it really comes down to, if it's less dense than water, then it will float, and if it's more dense than water, then it will sink.
OK, and so we've made something there, this piece of straw with plasticine on the end, that was just about less dense than water. So what happened then when Amanda was squeezing the bottle?
OK, so when we squeeze the bottle, we're increasing the pressure inside the bottle, and that's inside the whole bottle, the pressure's increasing. But the thing is water is very difficult to compress, comparatively. It's really difficult to compress water. But air is actually comparatively, relatively much more easy to compress. So by compressing the air inside the straw, you're making it smaller. So although it weighs the same, you've taken no mass away from that object, but it's taking up less space, so its density has increased, and therefore it's increased relative to the water, so it begins to sink.
OK, so when you actually squeeze the bottle, you squeeze the water in the bottle, because that can't be squeezed. It has to kind of take it out on something, does it? And that is the straw.
Yeah, exactly, because the air is so much more easy to compress than the water is.
OK, so then, this effect, where do we actually see this in the practical world?
This is actually how fish can control their height in the water. They have little sort of air sacs inside them, and they have muscles which compress those. So the fish is actually sort of changing its own density by compressing these air sacs. And it's also how submarines work, and it's how their ballast tanks work, where they sort of let water in to increase their density, and then they pump water out to decrease their density.
OK, so a ballast tank is really like this air pocket, is it? And they just kind of compress it however much they want.
Yeah, exactly. That's just how they work.
Wow, OK, right. Amanda, does that make sense to you?
Yes, it does.
OK, I mean, I've actually always wondered how submarines and fishes manage to do that. What about you?
Well, me too.
OK, well, it's been explained. OK, so how did you like our experiment?
I really enjoyed it, and it was totally amazing.
OK, and will you be going home and doing the same again with everyone you know?
Yes, I will.
Excellent, a convert. We make lots of them on this part of the show. Good stuff. OK, well, thank you very much to Amanda, who's at Colchester County High School, and also to Sheena Elliott, who will be back with us doing more kitchen science. So that's all from Colchester County High School, and we will see you again next time for some more kitchen science somewhere in the east of England. So until then, goodbye.
Thank you, Derek. Thank you, Sheena. And thank you, Amanda, our volunteer out there at Colchester High School, who were investigating the principles of a Cartesian diver. Now, one of the people who got it right was Hannah, who's in Essex. She was 6. But unfortunately, she was pipped to the post by Jocelyn, who joins us now. Hello, Jocelyn.
Hello.
You got it right. What did you find?
When we squeezed the bottle, the pen lid sunk to the bottom of the bottle, and when we stopped squeezing, it floated back to the top.
So now you know how submarine works. Brilliant. Well done. Thank you for doing the experiment. Well done. You've won yourself a copy of Living Science. All right?
Yeah.
Thank you, Jocelyn. Right, let's go back to Bob, because we're talking this evening about the deep ocean, and Bob's in Essex. He wants to ask you a question, Ron. Hello, Bob.
How are you doing?
Very well, thank you. What would you like to ask Ron about?
Oh, it's about the deep ocean trenches, whether there's any life at the bottom of them. I mean, we know there's been life around the vents on the ridges.
Oh, yes, hydrothermal vents.
Yes, but what life has only been discovered at that great depth? I mean, it obviously be bacterial or something similar, something very, capable of withstanding high pressure. And
OK, let's ask Ron, because we're a bit short for time. What do you think?
Hello, Bob. The basic problem with the ocean trenches, we're talking about 9, 10, 11,000 metres, is that it's incredibly hard to sample animals from down there. People have only been down there once, and they saw fish. There are very few nets. In fact, there are no nets that can go that far down. But so far, 4 species of fish have been found in these trenches, but 90% of the animals down there are holothurians, which are basically tube worms. So there is a lot of life down there, and you're right, there are also bacteria that live on the sea floor. The problem is we just haven't found most of it yet. It's not that it's not there, it's just that it's so difficult to actually see it.
Bob, we're going to leave it because we're a little bit short for time this evening, but thank you very much for joining us on the programme.
Thank you. Bye-bye.
Can I ask you, Ron, about those animals? How do they withstand that tremendous pressure?
Well, as has been said once before this evening, they basically can withstand this pressure because they do not contain air spaces. And if you don't have any air spaces, I think, as Jason so graphically put it, if he went down to a kilometre, he would implode and his skull would be crushed. This doesn't happen to the animals down there because they don't have the air spaces.
And what sort of weight of water have they got sitting on top of them? And when you bring them to the surface, why don't they do the converse and explode?
Well, again, they don't explode because they don't have air spaces in them. They don't have these swim bladders, which most shallow water fish have. So if you bring them up, they don't explode.
We are actually out of time, unfortunately, so it remains me to say a very big thank you to Ron Douglas, to Jason Hall-Spencer, and also David Klein, who appeared earlier. And thank you to you at home for giving up your evening and listening to us here on The Naked Scientists, and for everyone who took part in doing our experiment. It's been great having your company. Thank you to Phil for doing a great job.
Thank you very much.
And our production team, Holly Barclay, Anna Lacey and Petro Minch. Next week, it's our science question and answer show, and what that means is we sit here in the studio and we'll take any science question on anything. So you just send them in to me. Send them in this week. chris@nakedscientist.com via email is a good way to do that. And then what we'll do is put them into next week's programme. Good night.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.